All right, part number 2. About the meaning of herd immunity. So what do I mean by that, by meaning of herd immunity? So I just said that if you have a node that's vaccinated, but this node kind of doesn't exist for our disease spreading process, right? The disease cannot enter it, so the node cannot be infected, and the node cannot be infectious because of that, so it doesn't spread disease, which means that basically it's as if this node was deleted. So then the question is, what's the point in modeling this thing then? So we have this thing here. What's the point in doing it if if vaccinating a node is essentially the same as deleting it? We just have a smaller network. Can we just not do that and just generate a smaller network? So if we vaccinate like half a node, can we just generate a network that's half the size and be happy? Well, it's an interesting question, isn't it? And like this part of the plot looks like it might be the case because see, it kind of goes linearly down, so as if just the network itself is getting smaller. But then at the end, some interesting thing is happening because at the end, this curve is happening, and that's actually when the herd immunity is kicking in. Because if you look at that, the share of population affected drops almost to zero, not when everybody are vaccinated, but when about 70% of people, or I mean nodes, are vaccinated. That's for this particular disease, for this particular like fake disease, for this particular probability of propagation and the period of infectivity. But that's what herd immunity is about. So with 70% nodes infected, the disease cannot spread anymore. And that sounds like something interesting. So it sounds like it may not be quite about just having a smaller network. So how come? Okay, let's test it. Let's just model it. Let's do the following. Let's create a big network and then remove some nodes. And then let's create a network that's the size of, like of the same size that, yeah. So let's create a network of 200 nodes and remove like 100. And separately, let's create a network of 100 nodes and let's compare them. Make sense? So let's do that. But to do that, we need to be able to delete nodes. And right now in our code, we don't have a delete node part. So if we look at this part, we have like, we can add edges, we can delete edges, we can add nodes, I believe. Yeah, we can add nodes, but we don't have delete node. So let's add a delete node part. A new method, define delete node self and node. That's node to be deleted. So what should we do? All information about the graph is stored in two dictionaries, in gdict and in values. And values stores this information about each node, whether it's infected or not, and how long ago it was infected, and so on. And gdict is a dictionary of connections, right? It's probably somewhere around here. It's basically this part. It basically looks like that. So for each node, it contains a list of all nodes it is connected to. So we need to remove items from both dictionaries. Is it all? No, right? There is one more thing. Other nodes can be connected to our node. So first, before we delete all of that, we need to go through those nodes and delete reciprocal connections. Because remember, every time we add an edge, we tell node 1 that it's connected to node 2, and we tell node 2 that it's connected to node 1. So not only we want to delete the node, we also want to make sure that no node is connected to it. Okay, so let's do that. So let's go through all nodes that are connected to this node. Like, we actually have the list, right? It's stored in self. So like, let's call this node friends. For friend in self gdict all friends of this node. So for friend, should I be more professional and call it other node 2? Okay, for other Other is fine. For other in self-gdict node, so we'll go through all nodes this node is connected to. For all of those, self-gdict other, we need to remove node from this list. So remove node, right? So for every node to which the doomed node is connected, we look at the list of its connections and remove the doomed node from it. Let me actually rename this node to doomed node. It makes immediately, I think it makes everything more readable. Let's do other node. The art of not using commentaries at all. This way it reads like English. For other node in self-gdict doomed node, yeah, good. And so now all edges are taken care of, and we can just delete the doomed node from both dictionaries. So delete self-gdict doomed node and delete self-values doomed node, right? I think that's it. We don't have to return anything because we're just editing the object itself. So, okay, let's test that. Let's test that. So after gplot, let's do g delete node. Like, what do we have? We have 0, 1, and 2 here. Let's delete node 0. Uh-oh, it didn't go deleted. Oh, no, it did. Well, yeah, I didn't plot anything, right? Oh, yeah, everything's fine. Let me actually do print g. Okay, look, so originally it was a graph of 3 nodes. 1, 0, 2 was, 0 connected to 1, 1 connected to 0, 2 connected to nothing. And now once I deleted 0, 1 is connected to nothing and 2 is connected to nothing, 0 doesn't exist, right? Let me delete node 1, also works. Now 2 is connected to nothing, 0 is connected to nothing, 2 is connected to nothing. Good. If we try to delete a node that doesn't exist, we get a key error without much commentary, but that's because, like, yeah, the node doesn't exist. So conceivably, if we were writing if we were doing a more marathon, like longer project, marathon style project, so maybe we wouldn't be happy about that. So maybe we would go to here to delete node and do something like if the node actually doesn't exist. So if doomed node not in self-gdict, something like that, and then like whatever you do when errors happen. But like, let's remember that it's totally doable, but let's not do it now because, yeah. However, if you're doing like a senior project or a paper and you want to build a model, you may want to help your future self and write it in a little bit. Like, okay, what would you actually do here? You would probably do something like, you would actually cause an error. So you do raise, which raises an error, and then you would like indicate a type of error, like key, I think it's called key error, I don't remember, I think like that. And then here you would write a message like, a node like that doesn't exist. And now if you like, oh no, not key error. Oh, raise. Why? Raise K error. Did I make a typo of sorts? K error. Why doesn't my thing work? I'm trying to find a way to do it properly. Key errors and how to raise a key error. Okay, how to raise a key error. You do raise key error. Why doesn't it work for me? Where's my code? Why is my code key? Oh, because I wrote error. Okay, how's about double R? Thank you. Yeah. Oh, look, now it says a node like that doesn't exist, which is not too helpful because like we want to know which node doesn't exist. So we could do it like you can actually improve that as well. So you can do something like there is a way to make fancy strings, like you add a little letter F here, which is called an F string, and then here in curly brackets. And that's like I'm not even teaching that in the sense that if you want to learn to do that, you can read about that. But like be aware that it's totally possible. So doomed node like that. So if you now a node 5 doesn't exist. Well, actually, let's make it even more informative. Cannot delete doomed node. It doesn't exist. Yay. There's not a way, like it's not official enough. The language is weird, but that's the gist of it. That's how you do it. If you want to, if you need to. But for our purposes, like, that's fine. So, because I'm not being consistent right now, right? I don't have checks like that for any other. Like for delete edge, for example, I don't have a check like that, but whatever. Good, so we can delete nodes now. So back to our program. So let's have a tiny experiment here. So let's create a Barabasi network of say like 200 nodes. Delete say like 100. Let's do like 150. Delete 150 nodes from it and compare it to a Barabasi network of 50 nodes, right? G equals Barabasi 200 subplot 1-to-1 gplot. Nope. PLT subplot. Yep. Okay, good. Don't like the size of the figure. Let's make the size of the figure larger. PLT figure fig size equals what do I do usually? 10 by 5, something like that. Yep. Okay, so that's Barabasi network of 200. Then let's do another one. Like, okay, whatever. Okay. G, let's do it. G equals Barabasi 50. Gplot. Okay, so this is 50, this is 200. Now let's delete 150 from 200. For I in range 250, let's pick a random node and delete it. Oh no, let's you know what, because it may be hard, let's just generate a list of 150 nodes to be deleted. So doomed nodes equals np random. There is a way like, okay, let's do choice. The cool thing about np random choice is that we can run it with replace equals false. By default replace, oh, this is the old numpy. This is, where's the new numpy? This one? So by default, replace is set to true, which means that you can draw the same number twice, but we can set replace to false, and then we will pick every number only once. So like all nodes will be different in our list, which is what we want because we want to remove 150 different nodes, right? So let's do that. Doomed nodes equals random choice. What are the options? Everything from 0 to 199. So range 200. How many do we need? We need 250. And replace equals false, right? Let's print them. Print doomed nodes. Nope, doesn't work. What doesn't work? Oh, because I started for I in range. Okay, let's. I started a loop, but there is nothing in the loop, so let's comment it for now. Okay, so here are the 150 nodes, and supposedly all of them are different. Okay, let's just test. Let's try to take 201 node from 200. It says cannot take a larger sample when replace equals false. So it seems to be working, right? Returns an error if we try to do something that's impossible, which means that's probably working. So let's go back to 100. So okay, now the loop for I in, let's just go through all doomed nodes. For node in doomed nodes, let's delete it. G delete node. Okay, look at that. So here's what's happening. Look, they look nothing like each other, right? If we delete nodes randomly, we don't have the original, we no longer have a robust network. Does that make sense? Because look what, okay, you know what, let's look at degree distributions. We can do that. So let's, instead of subplot 1 to 1, 2, so like 2 by 1, let's do 2 by 2. And let's do this, but then plt subplot 2 to, it would be 3. Let's do a degree distribution of this one. G, how does degree works in degrees? G is a funny function that we wrote before. Degrees G, and we will do the same here. Plt subplot 2 to 4 degrees G. Okay. Aha, look at that. So now I need to change the size of my figure, which I can, 8 by 8. So originally we have this nice degree distribution where no nodes have degree of 0, because this means unconnected. A lot of nodes have degree of, actually no node has a degree of 1 as well, because every time a node is born, it's connected to 2 other nodes. Then most nodes have degree of 2, but then we have some really weird, like super central, super connected nodes that have degree of ridiculous, right? Like this node in the middle. Once we like use this shotgun approach to randomly remove a bunch of nodes, we get a network where most nodes actually have a degree of 0. And with this layout, they are shown on a ring, but all of these nodes are lonely, unconnected nodes. So we have like whopping, whatever, 20, is it percent or what? Frequency. Percent probably. Let me check. In the degrees thing, do I calculate just number or the degrees? I do histogram. No, that's the actual number, right? His degree equals +1, and we never, yeah, so that's actually the count. It's not the distribution. So out of 200, out of 50 nodes, because both of these networks are 50 nodes, whopping 20 something are not connected, and then a bunch more are one connected, and we just happen to kill the supernode. Well, or rather, it has no one to be connected to, so it's not, even if it survives formally, it's not a supernode anymore, right? So I guess you can see how herd immunity works, right? Even though we not only we take a bunch of nodes out, we also drastically change the distribution of degrees for the remaining nodes. And so instead of this hyper-connected network of 50 nodes, we now have 50 nodes, most of which are not connected to each other at all, which means that they're like in super social isolation, except they're not in social isolation. They just don't have any friends who would be also unvaccinated, and so they cannot be vaccinated. There are these two like last graph-like little like chicken paw kind of style thingies that can still be susceptible, because here we have unvaccinated, or in this case undeleted nodes still connected to each other, but that's basically will be all the disease can feast on, unlike the full network of 50 nodes as in the unedited case, right? Does it all make sense? Deleting nodes, vaccinating nodes is very different from not having these nodes to begin with. Yay! So this concludes part 2 of our today's exercise, and we're left with the most, because we're here on a tangent, and we're left with the most like fancy part, which is assertivity. And I will again stop the video and then restart it to have a third video on YouTube on this topic.